am your host Viraj Patil and my guest is Prem Mane. So today we are diving into the something that honestly affect every single of the your point. So tolerance in cloud computing we discussing about.
Thanks, Viraj, for having me. This is one of my absolutely favorite topics, and I think once you listen this, they will never look at the loading spinner the same way.
So that's a bold promise. Okay, so before we get deep into the technical stuff, let us see the scene. Why do we need to talk about fault tolerance? Like, can you paint a picture for someone who has no idea what it means?
Sure, Viraj. Basically, you are the CTO of a massive e-commerce company. Think Amazon or Flipkart. It is a peak of a big scale, and thousands of order per second, and suddenly one of your server goes down. In traditional setup, there is a disaster. The whole site crashes. You lose scores of the rupees per minute. Now imagine instead of the system keeps going, users feel nothing. The fault tolerance. That's fault tolerance.
So wow, so it's basically the system's ability to stay alive even when the parts of the die.
Absolutely. The formal definition of fault tolerance is the ability of a system to continue operating correctly in the event of a failure occurs in some of its components. It's not about preventing failures. Failures in cloud computing are inevitable. It's about designing system that survives them gracefully.
So failures are invaluable. That's both terrific and widely reassuring. So cloud computing like fundamentally flagrant at a scale.
At this At a scale, yes. You have thousands of servers, millions of processors, complex networks, and something will always go wrong. Where the question is, does that bring everything down, or does the system handle?
Okay, let us talk about what actually goes wrong. What kind of fault are we talking about?
So great. So we are talking about basically some faults comes from everywhere. Let me walk through a main categories. First, you have got hardware faults that there are very real. Your CPU can overheat, your RAM can develop bit errors everywhere. Individual random bit just flips from 0 to 1 randomly, even from the beginning, like cosmic radiation hitting the chip. Seriously, that's a real thing.
So, wait, cosmic radiation like space is affecting our cloud servers.
Yes, we can say that. It sounds crazy, but yes, high energy particles from space can cause where are called single event upset in memory chips. That's why ECC error correcting code. The method exists, but yes, the universe itself is a source of faults.
I love that. So, space is hacking our clouds. So, go on.
Then we have got storage faults, disk going false, error by bad sectors, complete drive failures, network faults, packet loss, disconnections, latency spikes, power supply issue, voltage fluctuation, complete power cuts. But then there are software faults, memory leakage, bugs, configuration error.
So, that's a really long list of things that can go wrong. How do you even begin to detect this?
So fault identification is the actual that very first step before you can record from anything. Modern cloud system uses what called monitoring and observability. They continuously collect three types of data matrices. First one is CPU percentage, memory uses, logs, detailed commas and events, and traces as it travels to multiple services.
So, if my checkout in e-commerce site slow tracking tells you exactly which part of that chain is for front end and payment gateway, the inventory system is being lazy.
Precisely, that's a perfect example. And top of that, cloud system use heartbeat mechanism. Every component basically sends a I am alive signal every few seconds. If those signals stops, the monitoring system knows something has died. It's literally like a heartbeat monitor in a hospital.
So that's a beautiful analog. And there is also machine learning involved in detecting the fault now.
Yes, there is. This is where it gets really exciting. Anomaly detection using ML can learn what normal looks like for a system, normal CPU levels, normal traffic patterns, and direct flag anything unusual. Even if it hasn't crossed a fixed threshold, it can catch subtle issue that simple rule-based monitoring would completely miss.
All right, so now we know the fault are detected. Let us talk about the big picture, the different strategies for handling a fault. Even seen the terms reacting, protecting, and adapting hybrid, and how can break those down.
Yes, just give me a second, Viraj. We will back to it. So, so think of uh, think of it's like imagine you have driving and it start raining. Reactive, it starts raining, you get wet, then you pull out the umbrella. Proactive is you check the weather app before leaving the and you bought the umbrella in case. And adaptive is that you have a AI co-pilot that continuously adjusts your driving based on the real-time road condition. And hybrid is all of the above.
That's the clear breakdown I have the even here. Here, let us go through the each one properly.
Reactive strategies are traditional backbone of the fault tolerance. They accept the fault tolerance that happens and focus on minimizing impact through rapid recovery. Two big ones are checkpointing and replication.
So I I love that video game, and uh, so cloud system crashes if like loading and save files.
Exactly, and the smarter the checkpoints, coordinations where all the parts of the system save states together.
Mm.
Basically, the cleaner the recovery, then there is a reduction, maintaining multiple copies of data so across different nodes or different data centers. If one copy fails, another takes over immediately.
So when we Google say that your data is backup, they literally means there are multiple physical copies of your files sitting in a different buildings.
Yes, and there are different style. Active replications means all copies are processing, requesting, and simultaneously. You get load balancing plus tolerance. Active standby it means one primary copy. They're waiting to take over a if the primary dies. There is also QCOM based application used in consensus protocol like Raft, where a majority of replicas must agree before an operation is confirmed.
So okay, what is about proactive strategies?
Proactive is my personal one because it embodies the principle prevention is better than cure. The classic technique is software rejuvenations, and this is fascinating. Over time, software ages, memory leaks builds up, file logs don't get releases, things get fragmented, eventually performance degrades and system crashes. Software reactivations means proactively restarting the system before it reaches to failure points, like scheduling oil change from your car.
So instead of waiting the engine to seize, you maintain it.
Absolutely. There's a primitive migration using predictive analysis. The system identifies nodes that surely eagerly sigmas signs of failures, risking error rates, increasing temperature, and moves workloads off those before they crash. You never actually experience a failure.
That's incredible. Yeah. It's like evacuating and building up because of structural sensor detecting the streets before anything collapses.
Perfect analogy. And AI is playing a huge role here. Predictive failure analysis using machine learning can analyze historical failure patterns, performance trends, and anomalies to predict which node is likely to fail the next few hours. This gives the system to migrate workloads proactively.
So, okay, what do you mean by adaptive approaches?
Basically, adaptive is about learning and adjusting in real time. Instead of having fixed rules, like restart if CPU exceeds 90%. Adaptive systems continuously turns their own thresholds and strategies based on what they observe. They might shift from a lightweight reactive strategy during a normal operation to a more aggressive proactive approach when they detect sign of unusual loads. It's essential a self-tuning system.
So, and hybrid just combines everything.
Yes, most production cloud systems today are hybrid. You have reactive mechanism as a safety net, proactive mechanism to prevent predictive failures, and adaptive mechanism to handle the unexpected. The real engine art is following where to use which one.
So let us zoom out a bit and talk about how the fault tolerance actually gets built into the architecture of a cloud system. What do these system actually looks like?
Great. So there are few core architecture patterns that every cloud engineer should know. The first and foundational is redundancy. Simply put in the words like don't have a single point of failure. If one server goes down, there is another one. If one data center floods, there is in another region. This applies to hardware, software, network path, and power supplies. Everything critical gets duplicated.
And that's why AWS has regions and the availability zones.
Exactly. Amazon, Google, Microsoft have data centers across multiple geographic regions, and within each region, multiple availability zones. Physically separated data. A failure in one zone doesn't cascade it to another.
And load balancers come into these pictures too, right?
Absolutely. Load balancer distributes incoming traffic across multiple servers. They are also perform health checks. Basically, if a server becomes unresponsive, the load balancer stops sending traffic to it and redirects the load to healthy servers. From the user perspective, nothing happened.
What happened microservers? I hear that the term thrown around a lot in the context of resilience.
Microservers architecture is a huge enabler of a fault tolerance. Instead of one giant monolithic application where a bug in one module crashes everything, you break the application into smaller, independent services. A failure in the recommendations service doesn't take down to checkout services. Each microservice can fail, restart, and scale independently. Kubernetes, the container orchestration platform, which was specifically built to manage this. It automatically restarts crash containers, scales services up and down, and routine traffics after a failure.
And there are patterns like circuit breakers too.
Yes, the circuit breaker pattern is borrowed from electrical engineering, where a dependent service where a dependent service is failing repeatedly. The circuit breaker tips it also sending requests to the following circuit immediately instead of returning a response or a grateful error. This prevents what called a cascading failure, where a failure in one service causes a chain reaction that brings down the entire system.
So that's elegant. Like instead of hammering a broke door, you just stop knocking.
That's a great way to put in, and the circuit breaker periodically sends a test request. Are you back up? And if the answer is yes, it closes the circuit and traffic flows again in the self-healing.
So let us go to the real world. You can talk about some famous cloud outages and what they thought about fault tolerance.
For sure, cloud outages are some of the most educational events in tech history. Remember 2017 AWS S3 outage? It's a classic one, an engineering typo, a command during a routine update meant to remove all or some number of small server accidentally removed a much larger set, but because of so many services on the internet dependent on S3, websites and apps across the world went a short break for a couple of hours.
So a typo took down the internet.
A piece of the internet. Yes, the lesson human error is a class of fault tolerance, and the failure was amplified because of tight coupling. Too many systems depended on services without fallback. This phase, adding the better safeguards. accidental large-scale deletions, and encouraging architects to design S3 available.
So what are the trade-offs in fault tolerance? Like sound like you would always want to maximum fault tolerance, but there is much catch.
There is always a catch. A three-way tension is better between reliability, cost, and performance. Replicant shows money. You are running two to three or more copies of everything. Checkpointing consumes storage and CPU. Proactive migration uses resources. These all have a cost, and over-engineering fault tolerance can actually hurt performance. Too much consensus, coordinations, too many health checks, too many failures mechanism can latency.
So it's about finding the right balance.
Absolutely. The key question is what does your application actually need? A video streaming service and a hospital patient record system has a very different fault tolerance requirement. One can tolerate a single glitch, the other cannot.
So service level agreement is also known as SLA define those requirements.
Right, a typical cloud service level agreement promises something like 99.9% uptime. That is called 49, that means less than 53 of minutes of downtime per year. Some systems largest 5 nines, 99.999%, which is less than 6 minutes of downtime a year. Achieving these numbers requires a serious layered fault tolerance architecture.
Okay, the last big topic where all this handling, what does the future of fault tolerance looks like?
The future is AI driven, autonomous, and energy saver. Uh, Basically, today, where adaptive systems humans are involved in designing fault tolerance or rules and thresholds, the generational is fully autonomous, self-healing and cloud system, where AI model continuously observes the entire infrastructure, predicts failures days in advance, and autonomously take corrective actions without human into the loop.
So that's almost looks like cloud becomes a living organism that heals itself.
Exactly, that the metaphor is used in research. Self-healing system is a real field, and the other major direction is energy efficient fault tolerance. Traditional redundancy is wasteful. You are running extra hardware that is sits idle 99% of the time, consuming power. Researchers are working on the smart fault tolerance that achieves the same reliability with significantly less energy waste. Using techniques like selective replication, where only the most critical data and processing are replicated, and intelligent scheduling of the proactive maintenance during a low usage period.
And with the edge computing become so big, IoT devices, smart cities, fault tolerance has moved to edge too.
Absolutely, edge computing brings unique challenges. Edge nodes are often in harsh environments, have limited resources, and can't afford the luxury of large scale and replication. Fault tolerance techniques needs to be lightweight and local, able to maintain critical functionals, and if the edge node is cut off from the central cloud for a period, autonomous vehicle are extreme example. The car onboard system must tolerate faults completely independently because there is no time for a round trip to a data center.
So the next question is the staker just keep getting higher. This has been absolutely mind blowing. So Prem, let's do the quick wrap up. If someone who just getting started the cloud computing, where the key takeaways for fault tolerance.
Sure. Three big takeaways is fault tolerance are not expectations, they are the norms. Designs for the failure from one day. Two, use a layer strategy. Reactive mechanism as a safety net, proactive as an adaptive mechanism to ahead of the failures. Three, fault tolerance is a spectrum. Matches your energy to your application, its reliability, requirements, and budget. You don't need NASA level fault tolerance for a block, but absolutely do for the banking system.
So I love it. Failure are inevitable, but getting engineering they have invisible. That's the magic the cloud fault tolerance. So Prem, thank you for so much for being the show today. This has been one of my favorite episodes.
Thanks for having me, Viraj. This was an absolute blast. Hope the listener found this interesting and useful.
And everyone to listening, if you enjoy the today's episode, so we will again thanks Prem to joining us and tells about his thoughts to our subscribers and our podcast listeners.
Thank you, Viraj.